So, well, I'll tell you what, let me give you the lab paper. I actually want to give you the lab paper, honestly, just to save a little bit of time tomorrow. And give you an opportunity to even write something on it, so we're ready to rock and roll. Go. You give one of those maybe. You give one too. Thank you. Okay, so on the front of the paper, honestly, there's just some writing. You can read it. It's not a bad idea to read it, but I'm going to skip over to the back. It's kind of where all the action's at. Now, it's actually the same diagram. But before you just kind of quickly redraw it, just kind of draw it with me, because what I want to do is talk to you a little bit about some of the nuts and bolts with the equipment. So if you flip it over to the back, again, yes, it's the same drawing, but almost want to kind of walk you through a little bit. Now, point C, and you can draw it with me, but point C, it's going to already be marked. It does make it a little easier just to get started. So point C is going to be marked, and usually what people do first, it's a great idea, is to measure that angle. Okay, angle ACB, or basically that main angle in there, you're going to measure that. And of course, you'll have your transit. And I should say that these guys right here are going to be also marked. They will be little poles. Okay, pretty easy stuff. Here's the part that I kind of want you to listen to, because it's not necessarily super easy, but you can do it. It's making this right angle. It's getting point D. Okay, now point D, you don't just want to just put the pole anywhere. You don't just want to plop the pole down and say, hey, that's a right angle. Here's what you want to kind of visualize, that you would have located point A, meaning you would zero the transit at point A, and then you would rotate the transit 90 degrees. You actually would force the transit to turn 90 degrees. And then your friend or your partner is going to put the pole in the ground as you tell them to move a little to the right or a little to the left. And you put the pole in the ground when they see you. Okay, so I don't want to say it's backwards, but it's a little different way of using the transit. Now, that pole is going to get pulled out of the ground and replaced with a cone. Okay, be careful though. Make sure you put a cone there. And then you're going to repeat the process over here. You're going to repeat the process with point E. Point E. Same thing. I kind of want you to envision yourself making a right angle, putting the pole in the ground. When your partner says that they see you in the transit, basically when that pole is on that line CE. Okay. Now, that pole, once again, gets pulled out of the ground, replaced with a cone. Okay, and now it's time to move some things. You always want to be careful before you move something, but you now are going to move the transit. You're going to move it over here to point D, and you're going to get ready to measure this last angle. Now, to do that, you'll find yourself needing to put the pole back in the ground, but this time at point C. And so that pole gets a workout, okay, because it kind of works itself through the lap. So we put the pole at point C, transit's over here, pretty basic stuff. You know that you're going to measure that angle. Okay? And then you're going to find yourself walking over here, put the transit in the ground again, and measure that angle. You got some people that you're going to be working with, so you can kind of keep each other straight before somebody moves something. Okay, but always make sure that you mark the spot with a cone. And start by doing most of the lab at point C. You don't move the transit until you have both of these marked, D and E, so you can finish up with those last angles. Okay. Now, it ends up taking most of the period, and tomorrow's periods are a little shorter, so that's why honestly we're going to start outside. So we're going to start, remember, by meeting between the B and C wings and sort of that walk-through area where they're doing some construction and whatnot, but we'll stay out of the way. Okay, so I just kind of want you to picture that right now. Picture yourself staying or not coming up to the classroom and make sure that your need is there. Okay, and we'll leave from there also. We'll leave from there. One more thing, there will be a real live alligator. Okay, so I know you thought it was just kind of for fun, but there will be a real live alligator, so you may not go into the passable area. But there will be another group working over here, okay? You'll realize when you get out there that it doesn't matter what side of the point you're on, you can still have a point C. So there'll be a group here, there'll be a group here, and quite honestly, there could be some groups over here too. You're all looking at the same 2 points, and I kind of have them like at a diagonal so that they still, well, of course, they're still the same, so you can still do the lap. Sound good? Okay. Keep the lab paper till tomorrow. There's nothing you really need to do with that, except I hope that you have it handy. And basically, you're ready to roll as we meet outside tomorrow at the beginning of the period. The homework, and I switch back to that. Here's some answers that we could not check last night. And maybe that we can talk about a little bit today. Now I checked number 14. And so the parallelogram diagonal. We certainly can talk about it if you want to. I want to talk about number 12. And something sort of seemed different last night for number 12. Now, you can kind of be honest with yourself. Sometimes people say, oh, it didn't seem different. Okay, so that would kind of be the first thing that we want to be careful about. Number 12, they mixed in a side-side angle. Now, when it comes time for the test, you're gonna have to first be aware of what scenario you have. So of course, you're not just rolling along on a test, just kind of using all cosines, because that's what you used for the problem before. And so number 12 is a side-side angle. It's not a sine angle sine. It just has to do with the 3 numbers that were given. Now, what that means, whether you figured it out last night or not, is that you have to use the chart. But here's kind of the reality. The letters that were used are different than the letters in the chart. I told you guys that I would never give you one like that. I guess I can kind of say I didn't, the book gave it to you, but I'm not grading you on it. I'm more just trying to help you learn that number 12 required the chart. Okay? If you didn't notice that, sort of join the club, but make sure that next time you do, and technically it ends up being a 2 solution type. Again, I even say, honestly, I'm not sure I expected that you got that. But if you did notice that it was the law of sines, good job. Number 12 is the law of sines. Right? The rest of them are the law of cosines. Is there something specific besides just kind of talking about it? Okay, good. I mean, normally you see a lot of success with these concepts, but if some number is different and you know that you're having trouble with something, I hope that you'll ask about it or get some help. And we're happy to still do that. What I'd like to do with the time that we have, and I kind of said at the beginning of the year, I don't like to waste time, is we're just going to kind of get started on your next application. Your next application. It's an assignment. It's an assignment. It's actually not due until Tuesday, so you can sort of just relax a little bit. It's not due until Tuesday. But I thought we would use a couple of minutes right now to just talk about these types of applications. In other words, something that might use the law of cosines or the law of sines. Okay, now letter A and letter B at the top are meant to just give us a little bit of a taste for these types of applications. Why don't we use our time and talk about those? It should be good. And then as you have time over the next couple days, you can start picking away at this. Okay, read letter A. If you didn't read it yet, at least read it. A little softball question there. Now you don't have to play softball, but do we have any softball girls in here? Or baseball, I know we got some baseball guys. You don't have to play baseball or softball to still understand the problem. It does say it's a square. Okay? It's a square. I'm having trouble drawing that, but technically it's a square. It does help to know a little bit about home base and first base. If you for some reason didn't know that, I can tell you. And then we have the pitching rubber somewhere. We'll say loosely in the middle, somewhere in the middle. Okay, now, don't assume things that aren't true. Try to take only what is given to you and apply it. Okay, stuff that's given to you is that you have a 60-foot side for your base path. Something that's given to you is that we have this pitching rubber that is 40 feet. Okay, so again, don't assume things that you aren't given. And what I'm really getting at is that you are careful when you realize that it's this distance that we're trying to find, but nobody says that it's equal to 40. Nobody says that it's the same as this one. Even though this angle down here, now this would be something we'd have to think about a little bit, this angle down here is definitely bisecting your corner. It's definitely bisecting it to be, of course, 45 degrees. But again, I say to you, don't assume something like this is 45 degrees, okay? That actually, believe it or not, is not true, but we're trying to kind of figure that out. So if you would say that that's 45, now you've made a decision that this is a 45, 45, 90. And it's actually not true, but part of the problem is to figure out what is true. Plus, I hope you just look at this and say, okay, side angle side. Okay? It's a law cosine application paper, so not a big surprise that it's side angle side. And so, one more time, we have the law of cosines. I hope you don't get tired of the law of cosines, but it does require the same setup. And it looks like you guys are doing a nice job with it. Just be careful sometimes when you do something over and over. You know, like punch that in your calculator that you accidentally don't type the wrong thing. Like make sure it's cosine of 45, not sine. It's the cosine of 45. You can play along if you want to get the answer again. I will tell you the answer, but you want to realize that the answer you get here, it does tell you, as we discussed, that you don't want to assume. Okay, so it does tell you when you get 42 and a half that indeed this side over here is not forming a right angle. It's not forming a right angle. And so again, this is not 45, 45, 90. Okay, I guess the pitching mound is a little bit forward. The pitching mound is a little bit below the middle of the field. Okay, pretty straightforward side angle side scenario. Let's look at one more. Doesn't hurt to read it. You'll learn a little bit more than if you just kind of wait. West Coast, San Francisco, water, okay, just get a little bit of an idea here. Now, do you know have you spent any time talking about bearings? Some people have, some people haven't. It's helpful to put like a north, south, east, west compass on your point, in this case on San Francisco there. And for me to try to help you understand it, to say 40 degrees west of north, okay, means that the second direction becomes your reference. It's kind of like this. I would start north, I would reference north, and then I would go west of that. And of course, west on a compass, in this case, north, south, east, west, would be to the left. Now, this guy right here, okay, this space right here, this is your 40 degrees, because I went west of north, west of that reference. You want to see if you can draw 10 degrees west of south. South is your reference. You want to feel like you're talking about this space, this tiny angle in here, as your 10 degrees. Now, even when I look at this with these arrows on the end, it's a little misleading because it's not like that the distance keeps growing. It's actually a point where your ship is located. So there's actually a point. Makes it a little easier to realize that it's this dashed line that we desire. We're trying to find the distance. Okay, and of course you've got some measurements that we can figure out, like these two distances, and how about this angle in here? Speaking of that angle in there, that's going to come out to be 130, maybe something to find. How's it going with those distances? Are you guys thinking about the rest of the information? What's this, 20 knots, 20 knots. Okay, if you don't have any exposure to that, that's still a rate. It's like a speed. So if we're going 20 knots, and you do that for a couple hours, then your distance equals rate times time. Now, it's a nautical mile. Okay, if that maybe caught your attention a little bit, a nautical mile is just a distance measured on the water. Do we have any sort of boaters, sailors, or Navy family? Okay, myself, neither, but I looked it up on the computer. A nautical mile is a little longer than a regular mile. It's 1.15. So it's still a distance, but it's measured on the water. And we also end up with a distance as well. Side angle side. Okay, again, kind of a pretty basic application, but side angle side. And that'll get you one more distance as you use the law of cosines. Oops.
15 knots.
Thank you. It would be 30 because it's 15 knots. So 40 squared plus 15 squared, use those numbers.
It would be 30 knots, not 15, because it's times tail.
Exactly as Jay said, right? But I wrote 15, right? It would be 30. Thank you guys. End up with a distance of 63 nautical miles. 63 nautical miles. How about this thing called knots? Like, why do you measure speed on water with knots? Anybody have any exposure to that? Well, I found somebody on the internet, you can always find something on the internet, that talks about why speeds were measured in knots, they actually still are measured in knots.
Sailboard, and that, because of the lead weighting, sat upright in the water. Didn't sink, but it sat upright. And that stopped it being dragged through the water. So when you chucked it overboard, it stayed still, and the ship sailed away from it. And you could pay out over this line, and at intervals along the line, in fact, every 14.4 metres, you would mark it with a knot. The first one had 1 knot, the second one had 2 knots, the third one had 3, you get the idea. And the unit of time was peculiarly 28 seconds, which was measured with an hourglass. So you turn the hourglass over, throw the log out, and when the sand ran out of the hourglass, clamp on the rope and say, oh yes, that's so many knots. Well, let's see how it goes. Let's get the rope ready. I think we're ready to heave. Could you start the hourglass now?
So, the rope is leaving the ship. And a knot keeps passing by his finger.
Okay, that's the end of 28 seconds. Well, let's see where we are. We're not on a knot, but just down here, not very far away, is this. What does it say? As you can see, it's got 4 knots on it. So we're going at almost 4 knots. Not very fast, but a nice leisurely pace. Now we've got a retriever. Let's test this peg. Give it a good jerk, and we should be able to reel it in fairly easily.
So you basically throw something overboard, and of course the rope keeps going out and out, but every knot that passes by in 28 seconds is the measurement of speed. Okay, 4 knots, not too fast, 20 knots, moving along pretty quickly. Okay, it actually was the way that you measured speed on the water before digital and electronic things. They still use the term knots, but obviously got GPS and digital things. Okay, a little something extra. That assignment is not due until Tuesday, so you have it. You can pick away at it if you have time. We actually have a little class time Monday. You'll have a little class time Monday. We will see you tomorrow outside between the B and C wing.